Okay, let's get started. Okay, great. Thanks. Thank you for coming. Uh, Today we're very happy to have Dr. Jing Liu uh, give today's colloquium. I just realized he's competing with the Space Weather Week uh, meeting for ongoing right now. So very good. We have a good turnout. And Jing received his PhD in space physics in 2012 from the Institute of Geology and Geophysics, Chinese Academy of Sciences. And then he stayed on as a postdoc for 9 months. Then he went to Japan to National Institute of Polar Research as a guest researcher there for a year. And then he came to HAO, joined us as a postdoc fellow in 2014. Currently, he's a joint postdoc fellow between HAO and the NCAR data simulation program. His main research interests include the ionosphere physics and also ionosphere data simulation. And this research is done last year.
Okay, thanks, Andy. Thanks for attending today my talk. Today my topic is observation and simulation of the ionosphere, density and time visualization. I benefit a lot from the collaborators and also other AIM members. They give me very lots of valuable suggestions on how to do it. Here's my motivation. SED is a subaurora enhanced plasma density structure, and the time of visualization is a polar cap enhanced plasma density. They are both the important elements of the high latitude ionosphere variability, which in turn affect the global energy and momentum budget. So that's why it receives lots of attention from both observation and numerical simulations. Even though lots of work have been done, there are many aspects of their formation and nature are still poorly known. Therefore, we undertaken a set of studies to try to provide some insight into the SED and the TOI. Here is Earth's upper atmosphere. That's a classic upper atmosphere. The upper atmosphere is very hot relative to the lower atmosphere. That's the ionosphere that resides in this hot thermosphere. Here I want to introduce several key parameters. The first one is NMF2, that is the peak density of the F2 region, and the HMF2 is the peak height. Another one is TEC, that is altitude integrated total electrical content from the bottom of the ionosphere all the way up to the plasma sphere. As we know, quiet-time ionosphere electron density shows a strong dependence of solar zenith angle. So the electron density changes smoothly from the day side into the light side and has a less structured. However, during the storm time, we see the polar ionosphere are very well structured. The strong interplanet solar wind and magnetosphere interaction produce this kind of dawn dusk electron field. This dawn dusk electron field generates the anti-sunward flow. In the front of this post-lunar cell, we typically observe this kind of storm-enhanced density structure that is called SED. SED provides an important source for this tongue-like structure that is called a TOI, which is elongated in the noon and the midnight meridional section. And the time of visualization can be distorted after reaching the nighttime or aurora oval.
Excuse me, the white is no measurement or it's just
TEC.
No, the white.
White, it's lack of data.
No data.
No data, yeah. Thank you. And it's distorted into this kind of enhanced density. It's called a boundary blob. Another important structure in the subaurora region I want to mention here is a subaurora polarization stream, which is located at the subaurora region where the electron density are very low. And SEPS has a very strong sunward flux that carries from night side to the day side.
Question.
Okay.
Day side is up?
Yes, this is noon. This is midnight, dawn, dusk. Yeah. All the figures show all the polar figures shown in my talk. I follow the same format.
So that's a very short moment of time, right?
Yeah, just a snapshot. Yeah.
Over what is the integration time? Or, I mean, the different measurements, or is it an instantaneous measurement on all positions?
It is a GPS TEC.
Instantaneous measurement at all positions?
Yeah. Yes, you can. Yeah, almost. Yeah.
And after like a few minutes, 5 minutes, it's already different, right?
Yes. This is a 5 minutes integration. Yeah, this is ground GPS receiver and the satellite. We have lots of pierce point and get combined to construct this map. Here I want to show the polar ionosphere evolution during storm time. This is from the TIGCM simulation of 2013 March and 17 storm. The background here is NMF2, and the factor here is a plasma convection. We can see the two-cell convection here. Yes. Oh, sorry. After the storm commencement, we see the positive storm effects start to build up in the affluent sector. And this two-cell convection also expand towards the low latitude. And we see this tongue-like structure was dragged into the polar cap. Again, we see the previous one is about 9 UT. And about 18 UT, we see the same structure. That means this 2 TOI occurred for this one day. Let's play it again. This two-cell convection and enhance the electron density. And the expansion of this two-cell convection, and also at the same time the build-up of mid-latitude source region drag into the polar ionosphere.
What altitude does this assume is the NMF2?
Okay, the outer cycle is 40 degree geomagnetic latitude.
No, what altitude?
Altitude, this is NMF2, that is at the peak height. So it varies about 300 kilometers.
Right, is there a particular one that's assumed for this one?
The altitude,
It's just whatever is calculated in the simulation. It's not,
It's a plot of NMF2.
Yes.
Wherever that may be.
So the altitude's going to change.
Okay.
Yeah.
That's what I was asking. I didn't know if it was consistent or Hemispheric.
Yeah, thank you.
Is there SAP in this because in the
Actually, this is TIGCM so simulation. We did not add the empirical SEPS model into this simulation, so it did not include SEPS structure here. But it do have the mid-lat trough-like structure that may be related to the plasma stagnation here. So it has a very low electron density here. The previous slides we show the 2D plot of NMF2. Here I want to show the profiles, the altitude profile of SED. The blue line is the altitude profile of SED relative to this black one is the quiet time. Compared to the quiet time, the storm time NMF2 was increased by a factor. This is NMF2 quiet time, and this is storm time by a factor of 2.5. And at the same time, the HMF2 was about 100 kilometers higher for the storm time. This is from Pfizer in Alaska. Alaska is a millstone hill incoherent scatter radar observed. This is the heavy black line for the SED profile, and the thin black line is also the quiet time reference. We see we see the NMF2 and the HMF2 are both increased. There are several mechanisms that have been proposed for the SED. The first one is the polarward expansion of EIA. That is the so-called the silver fountain effect. That's upward, the eastward penetration in electric field that rises at equatorial ionosphere upward, and then followed by the poleward expansion of the EI crest from this kind of SED. Another one is the SEPS transport, that is sunward transport by the SEPS. The third one is slow pole effects. That's expanded two-cell convection always generate a positive storm effects in its front. The fourth one is equatorward neutral wind that rise ionosphere upward and reduce the recombination. So the electron density increase there. The last but not least one is enhanced eastward electron field that operate in a similar way as the equatorward neutral wind by rising the ionosphere upward. So to sum up, the discrepancy of these mechanisms lies in whether the horizontal or vertical is dominant. Horizontal can be either the zero by the SEPS or the Meridiano by the superfounding effect. And another is a vertical, that is rise the ionosphere upward by the neutral wind or electron field.
What's the difference between the first and the last one?
You mean the first one and the last one?
That's also eastward. You said it was also an eastward electron field. Right?
Okay, yeah, that's a good question. Here is the first one involves the equatorward eastward electron field enhancement, that is rise the equatorward ionosphere upward and followed by the diffusion. And this diffusion then diffuse along the magnetic field line. But this one is locally enhanced. For example, at the mid latitude, just enhance the electron field. This is local. This is the equatorward, and then followed by the horizontal transportation. Yeah. Here I show example that has been done by Rodriguez et al. At 2009, published in JGR. They use the time-dependent ionosphere model simulation. The panel A is for the low-added zero electron fields. So the plasmas just follow this plasma's velocity. They have the plasma just experience pure zero motion. The electron density and the peak height almost do not change. However, the eastward electron field drives a polarward and also the upward drifts. We can see the electron density here. Electron density was increased by a factor of 2 after 2 hours running. At the same time, the HMF2 was increased from 300 kilometers to about 400 kilometers. When a westward electron field was applied, it produced equatorward and downward drift, so the electron density decreased here. I give a little bit more explanation here. For example, such as this is the magnetic field line. This is a high latitude and a low latitude, and one eastward electron field tends to produce the E cross B drift should be perpendicular to the magnetic field line. So it has an upward component and the polarward component. While westward, the E cross B drift, this is this direction. It has a downward component and equatorward component. When an upward component exists, it moves ionosphere upward. So we know the recombination are altitude dependent. When the ionosphere are moved upward, the recombination reduced, so the electron density increased. The westward operate in the opposite way. Our research goal is to understand the source and evolution of ionosphere SED and TOI and their UT and MF dependence. The model we use is the NCAR TIGCM. The convection electron field is from Weimar model that's driven by the interplanetary magnetic field. The data we used is a GPS TEC that Millstone here high-stack graded TEC with 1 degree spatial and 5 minutes temporal resolution. That's the TEC we use to construct the very beginning the TEC map. And also we use incoherent scatter radar from Millstone here and Poker Flat in Alaska. They can provide us electron density and line of sight velocity. Based on line of sight velocity, we can derive the electron field and also the electron and ion temperature here. Silver Dawn provide us the potential. The electrostatic potential are obtained from the spherical homological fitting of the line of sight ion velocities. And the fourth one is the ionosonde. It can measure the electron density from the bottom all the way up to F2 peak. So it can provide us reliable HMF2 and NMF2. The next one we use is cosmic topside TEC. That topside TEC is between the cosmic satellite altitude is about 800 kilometers. Another one is a GPS orbit is about 20,200 kilometers. So that's the outline of my talk. First, I will introduce the formation mechanism of SED and TOI. What's the cause for that? Followed by a discussion on how does the TOI evolve under different universal time and interplanetary magnetic field conditions. The last one, I will give a special SED event case. Here is the storm we choose is 2013. March and 17th. This is a relatively moderate geomagnetic storm. The semi-actual index is about minus 132 NT. The shaded area belongs to the interval when the SED occur. This part is the global GPS TC map during the shaded area, the shaded interval. This is the absolute difference between the storm time and quiet time. The blue area at high latitude means depression in the total electron content. So we see the negative storm effects dominate at high latitude and positive storm effects at the middle and lower latitude. As in the following 2 hours, the positive storm effects was intensified here. And another 2 hours, we see this positive storm effect was further intensified, and at the same time we see the polar extension of this very tiny enhanced TEC here. That is streamed from from North America all the way to Canada and across the polar magnetic pole. We see the conjugate effect in the southern hemisphere in like this very tiny enhanced structure. This kind of global GPS map tend to obscure what's going on at high latitude in order to give a better visibility of the high latitude. Here is a polar projection of the GPS data TEC. We see the SED and also TOI and the boundary blob. This figure that I was shown in the second slide. The right hand side is from the TIGCM simulation. We see the TIGCM did a good job in capturing this enhanced density here and the time of realization and the boundary blob. But it also tend to overestimate. I mean, the TIGCM model tend to underestimate the negative storm effects in the afternoon and the nighttime sector, and also in the morning sector. Since TIGCM can capture main structure of the enhanced density, we use the model to do some term analysis for ion continuity equation. This is a well-known ion continuity equation for the F2 region. The left-hand side is change rate of ion density. This is a production. This is loss, and this is a transport term. Transport term includes electro field and neutral wind and ambipolar diffusion transport. The E cross B drift also has a vertical component and a horizontal component. Before looking at each term, it may be beneficial to look at how these parameters varies during storm time. It's not surprising to see that NMF2 has a similar structures, the TOI structure as the TEC. Also, this enhanced NMF2 in the throat region was accompanied by the upward ion drift here, and this ion drift almost upward in the daytime and also downward on the night side. This upward ion drift leads to the increased HMF2 and also lower HMF2 in the light side. That's maybe the E cross B drift effects may be balanced by the equatorial neutral wind. Here we see this is the neutral wind. the neutral wind in the throttle region is almost anti-sunward. That is because of frequent ion-neutral collision. So the neutral wind in the throttle region is also anti-sunward. That means the polarward. Besides the disturbance in the neutral wind, we see the neutral composition disturbance. That is very obvious at high latitude. Here is the result from the term analysis for ion continuum equation. This column is for absolutely NE changes at the top side and the bottom side. We define the top side as the ionosphere where above the peak height. Below the peak height, below peak height, we define it as a bottom side ionosphere. This column is for the electron density change rate caused by the chemical processes. This is the electron density change rate caused by the neutral wind effects. This is the electron density change rate caused by E cross B and ambipolar diffusion. We see the electron density, the chemical process are mainly operative at the bottom side ionosphere. That's because it depends on the O to N2 ratio. Both O and N2 decrease with altitude, so it's lessen the impact of O N2 ratio changes in the topside ionosphere. This is for neutral wind. As mentioned in previous slides, the neutral wind is polarward, so it pushes the ionosphere downward. Taking the electron density pressure gradient into account, this downward motion will reduce the electron density in the top side ionosphere and increase in the bottom side ionosphere here. The E cross B drift operates in opposite way as the neutral wind, since it raises the ionosphere up. Ambipolar diffusion acts as a passive force that mediates all the other three processes. Now let's look at it only in the top side ionosphere. We know that the only dominant one is the E cross B transport effect. E cross B is a dominant one for producing this kind of enhanced density. But in the bottom side ionosphere, both neutral wind and ambipolar diffusion are important. We know the TC mainly comes from the top side ionosphere. So we further decompose the E cross B transport in the top side ionosphere as a horizontal component and a vertical component. This one is a vertical component. In the throttle region, we see it here compared with the horizontal one is much stronger here than the horizontal one. But in the polar gap, especially the light side, it produces a kind of downward drift, so it reduces the electron density here. But horizontal component still has a positive effects to the TC variations. This is a look at it as a fixed pressure level. Let's look at how this term varies at different altitudes. This is a latitude correspond to this latitude slice at about 14 log time. And this is again the electron density changes along this latitude slice, and the photochemical process induce the electron density change rate. Here we see the aurora precipitation effect. This is the neutral wind. It reduces the electron density in the top side and increase in the bottom side. And the ambipolar diffusion is increase the electron density here. And the most important one is the E cross B transport. The top side ionosphere was greatly enhanced by this E cross B transport effect. It's much larger compared to these two. It's much larger than the horizontal component.
Excuse me, why E cross B transport is in units of centimeter minus 3 second minus 1?
Oh, this is, sorry, I forgot to mention. This is a
velocity. It should be velocity.
Absolute difference. Storm time, quiet time, the difference.
No, I mean, why E cross B is in this unit? It should be velocity, right? Centimeter minus 3 second minus 1?
Yeah, this is a change rate. Oh, this. Oh, yeah. If you do a time integration of this term, you should. we should get that.
Change of those things due to that process.
Yes, yeah, exactly. Here is my summary. In the third region, upward E cross B ion drift are the most important process for the SED formation. And the horizontal E cross B ion drift plays an essential role in transporting plasma to form the TOI. Let's go to the second part. We then look at the UT and MF dependence of townization. Here is a case we choose for this kind of study. This storm occurred for the October and about 13 and 14, 2012. The first TOI occurs in the main storm main phase or early recovery phase, when the geomagnetic activity are more intense. We see the KP is about 6 here, but the TOI here was weak. How about but for the second TOI for second period, when the KP was about 4, that means the geomagnetic activity are weaker, but the TOI was stronger here. So this means that the stronger geomagnetic activity does not necessarily mean stronger TOI. Here is the GPS TEC map, and superimpose this contour is also super-down derived potential. During this period, the MFBZ has a magnitude of -10. That's pretty strong. And also BY is about a change gradually from positive to negative. We see the town-like structure is weak. The peak density is about 10 TSU. However, the same color scale, the second one, we see the MFBZ is very weak, is quite close to 0. BY is also weak. That's a very weak magnetic activity, but the TOI intensity are stronger. It should be mentioned here, the TOI occurred at different UT. Previous one is about 9 UT. This one is about 20. So at least 2 factors were operative here. One is a UT dependence that determines the basic structure between the magnetic and the geographic pole. Another one is the interplanetary magnetic field that determines the driving force. I mean the storm driving force. So how to isolate or separate these 2 effects contributions? We performed a set of experiments. The first one is we just run the model for 24 hours. We set BZ equals -10 and BY equals 0. Based on this result, we see that TOI intensity reached its maximum at about 4 hours after MFBZ southward turning. So we check the UT dependence for 4 hours running under this kind of condition for each UT. That means, for example, for 24 hours, we run 24 times to check the model result at the end of each run. The third one is the BY dependence. We change the amplitude of BY and its direction to test it at a fixed UT to check the model result at the end of each run. Here, another thing I want to mention, all the models are run from initial condition, BZ equals 0, BY equals 0, to make the model reach a stable condition. Here is the TOI evolution for the southern hemisphere. The background is NMF2. We see as time goes by, the magnetic pole and 2-cell convection pattern that's rotate anti-clockwise with respect to the direct geographic pole. At the same time, the 2-cell convection follows a similar behavior. Another thing, we see the mid-latitude enhanced density that gradually build up. At about 4 hours, the TOI intensity reach its maximum here. But then further, you see them weaker. That's because neutral composition start to decrease the electron density. Here is the TOI UT dependence for the northern hemisphere, or 4 hours after storm commencement. The only difference here is the UT. we see the strongest TOI corresponded for the 20 UT. When we see these two cell convection are more tapped toward the mid-latitude, and also the mid-latitude source region here is stronger than the other UT. This is for the northern hemisphere condition. How about for the southern hemisphere? We see that this, in the southern hemisphere, the TOI is stronger at 16 UT. When these two cell convection are on the light side, I mean, on the light side, however, the source region occurs at a relatively higher altitude. So more plasmas can be dragged into the polar cap from this stronger TOI here. This is for the BY dependence. This is for the northern hemisphere and for the southern hemisphere. We see, compared to the BY equals 0, this BY has a larger amplitude. We compare the TOI intensity here with respect to this one. So larger BY magnitude tend to decrease the TOI intensity. That's because the TOI become more twisted. Another one, when BY has a negative component, the dawn cell becomes larger, so it pushes the entry region of this TOI into the later local time when compared to this one. This is for the positive BY. The entry region is located at the earlier local time. This is for the northern hemisphere. The southern hemisphere, almost the opposite conditions occurred in the southern hemisphere. That is, for the negative BY, the dusk cell becomes larger than the dawn cell. Here is a summary for the second part. TOI tends to occurs preferentially at the UT when the high latitude ion convection is closest to the mid-latitude peak density, so more plasmas can be transported directly into the polar region. The UT and MF orientation dependence of TOI is different between the northern and southern hemisphere because of different separation of these two poles, and also difference in the mid-latitude peak density and location and intensity. These two bars are behaved as what we expected. This one I will introduce a special case. The normal case is we observe both enhancement in TEC and NMF2. Here we see the enhancement only in TEC, but not in NMF2. This is storm. This is the most recent storm. This is quite intense. The semi-match index is about -234 NT. The shaded periods also denotes the interval when the SED occur. We see this kind of enhanced density structure here. This is the so-called SED, very weak tongue-like TOI structure along the anti-sunward flow here. The SED was gradually eaten away by the neutral composition effect. We see the much weaker in the falling period. At about 19 UT, with the magenta cross denotes the location of Millstone Hill. Millstone Hill was located exactly at the base of this SED. Here's the result from Millstone Hill. This Ionosphere, the NMF2 and the HMF2 are from the Ionosphere observation. The last one is a TEC, also in the same location. Here I want to do a little bit more explanation here. This blue one is a GPS TEC. The bottom one is calculated by the integration of the Ionosphere merit electron density from the bottom of the ionosphere to the F2 peak. The top side TEC is calculated by the subtraction of bottom TEC from the GPS TEC. So we see this jump-like enhancement here. Jump enhancement of TEC mainly comes from the top side. The top side contribution is about 8 TECU. A little bit enhancement in the bottom side ionosphere. At the same, the NMF2 here was much weaker than the quiet time reference here. This is the dashed line is the reference value, but HMF2 was increased here. The cosmic satellite is just passed over this SED region. We see this spike-like enhanced SED here. So the millstone in coherent scatter radar give a better vision of what's happening at different altitude. We see the electron density was decreased in the lower ionosphere, but increase in the top side. This our explanation is as follows: the electron density decrease here leads to less downward heat conduction, so it traps the heat in the top side ionosphere. So the trap of heat in the top side ionosphere resulting in the increase in the scale height in the top side ionosphere. The increase in scale height changes the profile so the electron density profile in the top side becomes steeper. Previous one is like this, then it's like this one. So that's electron density enhanced in the top side ionosphere. So this is a summary for the third part. There was a large plasma density enhancement in the top side ionosphere, but not near F2 peak. The F2 peak is a negative storm effect. This produced an unusual case in that there was a SED in TEC, but not in MF2. The TEC enhancement mainly occurred in the top side ionosphere was strongly related to the increased plasma temperature and consequently plasma scale height. Okay, thanks for your attention. Okay.
Is there a seasonal dependence, like you might expect in the summertime when the northern hemisphere is pointed toward the sun, that it might be more likely to pull in a tongue of ionization from?
Yeah, I think so. Actually, we have we did that kind of simulation, but it not show the result here. It has a seasonal dependence. Yeah, because of the solar zenith angle dependence of the source region, the mid-Atlantic source region. Yeah.
So in this model, the E-cross-P drift is empirical. You just measure it, or you derive it somehow.
Oh, it's self-consistent calculated. Yeah, the TIGCM.
But that requires connection to the magnetosphere, right?
So the highlighted too.
Highlighted, we use a Weimar. Yeah. Sorry, I saw that you mentioned the middle and low latitude. Yeah.
It's an empirical electric field model that depends on magnetospheric conditions.
Yes.
That the E-cross-P drift is calculated knowing what the electric field is, and of course the magnetic field.
So did you say in the last case of SED, did you say the plasma temperature is high because the downward, because the heat conduction is low?
Yeah, that's one of our explanation. Also, we cannot exclude the external heating source, such as the rain current heating the superthermal plasmas injected into the ionosphere. That could also be possible. Yeah, it could also possible.
So, and also when you did the IMF dependence,
Mm-hmm.
so why do you only look at the B-type dependence, not the dependence?
Yeah. For this study, we only look at because BY dependence and UT dependence operate almost in a similar way to change the two-cell convection pattern. The relative location of two-cell convection the relative location between the two-cell convection and the mid-Atlantic source were modified by both UT and IMF. So I want to isolate this.
To answer your question, when BZ is northward and BZ is bigger than BY, there's no tongue of ionization. So there's no point in doing that.
What about the intensity of BZ? Maybe a lot bigger negative BZ, but produce stronger.
Stronger BZ. On the one hand, it can increase the two-cell convection, but it also produced more Joule heating and own neutral composition changes. So it's kind of balanced.
And also, how do you tell the difference between boundary lock
Yeah. Yeah. Actually, boundary blob is a transport effect from day side along the polar across the polar cap and into the nighttime auroral oval. But the auroral oval, typically we mention auroral oval is auroral precipitation produced enhancement, electron density enhancement there. And also the boundary blob occurs mainly in the F region. However, the auroral precipitation in the E region. So that's the difference. Yes, exactly. Yeah. If you use the incoherent scatter radar to do the elevation scan, you see the two peaks. One is in E, another in the F. Yeah.
And the TOI usually didn't catch the SED is the one kind of in the middle of the two cell, right? Kind of the plasma, high plasma you brought in from the mid latitude.
Yeah.
And the TAN is
in the polar cap.
In the polar cap region. So and you mentioned in the later studies you mainly was focusing on the SED effects. How about the intensity of the TAN? What does that depend also on the orientation, or I don't know, what does it depend on? What determines the outside?
You mean in the subauroral latitude?
Yeah, I mean, what determines the how much plasma density goes out or wrapped around in the TAN area?
Yeah, in the subauroral, I think for the SED that is E cross V, maybe neutral wind, especially the neutral wind may also be important at the subauroral latitude.
Okay.
Yeah, it's hard to tell which one is dominant, and also neutral compositions also was operative during storm time. Is also quite strong.
Okay.
Yeah.
And they do not always appear as like if you have a SED, does that guarantee you have a TOI?
Yes.
You always observe it too.
No.
Okay.
You can see a CD, but sometimes you cannot see TOI. Yeah.
Can you go back to the slide that shows that each term for the bottom side and
Okay.
the side?
This one.
Yeah, this one, yeah. So for example, when you look at the top side, when you look at that ME, and then you use the 4 terms, and I don't see the added there can explain the big, the red area, for example.
I see.
Where does that come from?
You mean when we add this do not equals this one? Yeah, this one is absolute difference, but this one is for example, electron density change rate. This.
So accumulates over the time, right?
Yeah.
So if you look at the red area, so if you see an area also, maybe not that strong, but accumulates over the time, should be maybe it's in the equals this one.
I'll do that one. What all the terms are on a snapshot of one particular routine, whereas the delta energy is the integration over time, and those terms aren't necessarily the same if you say that 5 minutes before.
Okay, maybe so that red maybe come from E cross B, because of the E cross B.
You can't really tell from this approach, but it's likely.
Yeah.
It's a weakness of the diagnostics process.
Yeah.
But you could make a plot on the left that was volume per second.
Yeah.
That would nearly be the sum of all those things.
Okay. Yeah, snapshot of this.
Wouldn't prove anything because it's just the sum of all those terms.
Yeah.
So how do we connect that term analysis to the actual phenomenon?
So I'm serious at particular point. Then look at time
That's the nearest answer the doctor to do.
So did you say that SED could happen more often than TOI, right?
Yes.
So my understanding
Yeah. Yes.
And then TOI is the horizontal
Transport. Yeah. 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 Yeah.
So that means horizontal transport. So that's like to happen then the vertical.
Yeah. Yeah.
You saw
Yeah.
that in the second study.
Yeah. 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 Actually, it's quite common. That because of the neutral composition, you have sometimes eta weight SED when it enter into the polar cap region. So.
For it to give a chance to
Yes.
horizontal transport.
Yeah. Yeah. Exactly.
The UT has to be right. The Y component has to be right. Everything has
So
to be
then
right.
it can pull into the polar cap.
It's relatively easy to lift it up. It's pretty hard to move it across. So
Actually, I was looking at this, and then even from the snapshot, the full snapshot of the tendencies, it seems that you would, if you add them up, you would get a negative tendency, right?
You mean?
Yeah, I mean in this area, if you add, because I look at the scale, they're all similar. If you add all this up, will you get a negative tendency instead of?
I don't know whether we add this one into this one. I don't know. Maybe I need to do.
I mean, that's a snapshot of all the tendencies.
Yes. Yeah.
Right?
Yeah.
I think what you'll find is they're actually slightly displaced too. Because this is evolving in time, so the red doesn't actually fit right on top of the blue.
So they may not offset or cancel each other.
I think maybe it's better to add another term to include all these four terms.
All
Yeah.
the
Yeah.
terms,
Yeah.
Yeah, and also similar for the
Bottom side. Yeah.
bottom.
Yeah.
So the wind contribution is it refers to the neutral wind?
Yes.
This wind contribution, does this refer to the neutral wind of neutrons?
Yeah.
But you would expect on the top side it's completely decoupled, or the plasma is decoupled from neutrals on the top of.
What do you mean of coupled to neutral?
It's just the neutral wind, in this case, pulling the ions down the field.
Or this is along the.
Yeah.
I think you did some projection along the field line.
Yes. Yeah.
The ions aren't following the wind. They're just being pushed up and down the field line by the wind.
Yeah.
And I think so much of these phenomena are not exclusively, but a lot of these things that intuitively you look at something with a tongue or a balloon or something and you think transport. You think I took something from point A and moved it to point B, because that's our analog.
Mm-hmm.
You know, if you see a cloud of smoke into the room, you know it didn't appear, it's transported.
Yeah.
In the ionosphere, so much of this stuff is the result of things being pushed up or
Yes.
down.
Yeah. Yeah.
Either by E cross B forces or neutral wind forces.
Yeah.
And when things are pushed up or down, they change.
Yes. Yeah.
Decreasing the density of the interaction with the chemical terms.
Yeah.
And even the chemical terms can be thought of as pushing up and down because of increase of N2 density is really a big bringing up the motion of the heavier species.
Yeah.
And what is the correlation with auroral activity?
Or you mean auroral activity correlated with what? With SED or TOI?
I mean, whether the enhancements are strongly correlated or not correlated with the occurrence of aurorae.
Yeah.
Are they correlated or not?
Yes. All these are weak storm study, or moderate storm study.
If you get more precipitation, the electric field's going to be stronger. So that's one of the reasons why people move to
I would speculate that in really big storms, you may not see this sort of tongue feature as much.
Yeah.
Partly because it's just going to be a more incoherent, messy picture.
Yeah.
You get a big storm, things are changing rapidly.
Yes. Yeah.
It almost seems like the optimum condition for forming these tongues is when you have sort of modest,
Mm-hmm.
steady,
Stable. Yeah. Yeah.
so that the tongue can build up.
Yes.
It's like, you know, it's stirring a cup of cappuccino.
Right.
You don't want to get too much more into that, it tends to destroy the top.
Right.
Yeah. Another question: how strong are the fluctuations within, for example, the electron density? I mean, to what extent is what is actually the smoothing length scale of these pictures that you show us here?
You mean the electron density enhancement relative to quiet time reference?
I mean, I'm really talking about the resolution, spatial resolution
of
these pictures.
2.5.
Are they a result of averaging?
This is the TICM 2.5 by degree. That about 200 or yeah.
Okay, and there are strong fluctuations on smaller scales, no?
Yes, I think so. Yeah, yeah, but we cannot resolve that. Yeah, yeah.
The one thing we found is that in the older version of the model, that was at lower resolution, it was difficult to even create these structures. And at this resolution, we at least get something that's plausible for these large-scale pictures.
Yeah.
The model can't resolve the small-scale instability simulations that we've done.
So from observations, what's the characteristic cross scale of this estimate? What's the width, the physical width?
Put a figure up to you have.
This is yeah, here we see about 5 to 10 degree.
But in
Yeah.
terms of absolute numbers, I think that's completely wrong, right? I mean, the right one has much stronger absolute of changes.
From the model.
The model has much stronger changes.
This one?
Uh-huh.
Yeah. Yeah, the positive is stronger, but negative underestimate. Yeah.
Something you see in that data, I'm curious, you know, missing data seems to follow the auroral oval, or where we think the auroral oval should be.
Yeah.
So I'm wondering if that, when you're right under the auroral oval, maybe the GPS measurements aren't working right, and consequently they discard the data from the database.
Why would you think?
Well, when you have changes inside the structures that are in the auroral, it's causing scintillation on the GPS signals.
And then they
Yeah, so when the scintillation is too high, it loses loss.
You don't have much data.
see what I'm saying?
And each one of these
See that white?
specific signal
See,
patterns.
you can almost see the auroral oval in the. Look at the center
But
left.
it's like it's
You
see that white
whole
spot?
electron density. So
It
Right,
lines
so you've
up
got
with
signals
where
that
the
are in all
model
different
thinks the
directions
auroral oval should be
over
as
time.
represented by the red
And they're
spot.
taking that into account as they make the disposal times.
but
They're doing a vertical projection
this
on
means
it.
that even this integrated value is extremely disturbed by the
Yeah, so the GPS receiver loses loss if you have that thing.
I mean, you can do an integrated value.
Yeah, so if you have enough scintillation because the structures are so big, if you have enough scintillation all around, your GPS signal can't track anything, or your receiver can't track any satellites at that point. If it doesn't have at least 4 satellites, then you have no information.
But you can even show one, even one pass is fine.
Yeah, it still loses the position lock, so it depends on which direction it's looking as well. Some of that also depends on physically where you're located, because there's not as many receivers in the polar cap, because there's all that ice and not land. Yeah.
Okay. Thank you. Thank you all.